Swayam Prabha. Digital India. Educated India.
So good morning to all of you. We will be continuing our discussions regarding the drift flux model, the things which we were doing in the last class. What we did, we discussed about the advantages of the drift flux model and the basic concepts, the concept of drift flux, how it modifies the different mixture parameters, namely the void fraction and the mixture density, the local velocities and so on and so forth. And so, we understood that if we have some idea regarding the estimation of drift flux, then once we can incorporate drift flux into the equations which we had discussed in the last class, then we will be in a position to predict mixture properties much more accurately, and accordingly we can predict the hydrodynamics of two phase mixed flows as well as transitional flows in a much more accurate fashion. So, today we will be continuing our discussions regarding the different ways, or rather the approach to estimate J21 by using different kinematic constitutive equations. Okay. So, we will be discussing basically the kinematic constitutive equations to estimate J21. Now, in this particular regard, I would like to say one thing, that there are basically two approaches in order to estimate this kinematic constitutive equations. Okay. Now, one thing is for sure, that this particular model is particularly more useful when the relative motion, it can be determined by a few key parameters and it is independent of the flow rates of each phase, then only it is much more useful. Now, usually there can be two approaches to find out the kinematic constitutive equation in order to estimate J21. Now, what are the two approaches? One can be that to consider the mixture as a whole, okay, and then what we do is that we start with the mixture field equations. Okay. So, the two approaches, the first approach is that we start with the mixture field equations and then we apply, let me write down, start with mixture field equations and then apply various constitutive axioms, or rather various constitutive laws to the mixture Now, this is one approach and this seems to be quite logical. What we do? We consider the mixture as a whole, because in this case we have not concentrated on the individual, or rather we have not concentrated on the individual phases. What we have done? We have concentrated on the mixture as a whole. So, what we do? We concentrate on the mixture and then we try to apply different constitutive axioms to the mixture as a whole without considering their individual movements, okay, or rather without considering the two fluid model. Two fluid model means what? We will be dealing with it in much more details in the next chapter, the separated flow model. That means, we would be considering the two phases separately and we would like to write down the momentum, the continuity and the energy equations for the two phases. Okay. So, the first approach is we do not consider the two fluid model, we consider the mixture as a whole, and in the mixture field equations we use different constitutive axioms and which is applied to the mixture as a whole and it is independent of the two fluid model. This is one approach. The second approach is that you consider the two fluid model. Okay. In this particular thing, the necessary constitutive equations, just underline this. The second approach is that necessary constitutive equations obtained by reduction of two fluid model. So, this is the second approach. Okay. In the second approach, what we do? We consider the two fluids separately in whatever way they are mixed. Okay. And then considering the two fluid model, we try to arrive at the necessary constitutive equations. This is the second approach. Now, logically when you think, it will, you will always be tempted to think that maybe the first approach is much more logical and that should be used, because here we are considering the mixture properties as a whole. Okay. So, logically you will think that, well, we should consider the mixture field equations and then we should apply the various constitutive axioms to the mixture and it should be independent of the two fluid model. But if you notice properly, you will find that there are certain problems in using the first approach. Now, what are the problems? The first problem arises from the fact that the two phases are generally not in thermal equilibrium. Now, when they are not in thermal equilibrium, we cannot define a particular temperature for the whole mixture. Now, if we cannot define a particular temperature for the whole mixture, then in that case we cannot define the mixture properties as a whole, is not it? The second thing is that we will also notice that the kinematic and the mechanical state between the two phases, that is greatly influenced by the interfacial structure and their properties. Is it clear to you? So, therefore, we find that since it is sort of since the interface properties they are changing, or in other words, the point is, under certain flow conditions you are having bubbly flow, under other flow conditions you are having slug flow. Okay. So, therefore, we find that whether the dispersed phase exists as bubbles or as Taylor bubbles or maybe as churn sort of thing, this influences the constitutive equation. This influences the mechanical and the kinematic state between the two phases. So, as a result, if you consider the mixture as a whole, then in that case we are not free to observe what is happening between the two phases, how they are distributed, etc., etc. Is it clear to you? So, therefore, we find that this first approach using the mixture field equations and then applying the various constitutive axioms to the mixture, that usually it is not very preferred. Okay. And for most of the cases we obtain the constitutive equations by reduction of the two fluid model. Okay. Now, in order to use this, or rather to incorporate these particular effects, the effect that the two phases may not be in thermal equilibrium, the kinematic as well as the mechanical state is greatly influenced by the interfacial structure and their properties. In order to account for these particular factors, we find that it is simpler as well as more realistic to obtain the equations from the two fluid formulation rather than the former approach. Okay. So, accordingly what is usually done? Usually the two fluid formulation is done, the momentum equation for the two phases are written down separately, and from that particular momentum equation, naturally those momentum equations will be considering some particular term which arises due to the relative motion. From there the relative motion term is obtained and it is accordingly some constitutive equation is proposed for it, and that is used in the drift flux model. This is the approach which is used. Now, is this portion clear to you, or should I repeat this part once more? It is clear to you more or less. So, therefore, what we do, you remember one thing, that in order to estimate J21, there are usually two approaches that we can use. One is we consider the mixture as a whole, and then from there we can find out the constitutive equations. Now, if we have to do this, then the mixture has to have more or less uniform properties throughout. But what we find? We find that generally the two phases, they may not be in thermal equilibrium, and moreover their kinematic as well as their mechanical states, it is greatly influenced by the structure and properties of the interface. So, therefore, when the interface changes, this kinematic state, that is also going to change. Now, if that happens, then in that case we cannot derive an accurate constitutive equation by using the mixture field equation. What is more accurate? We take up the two fluid formulation. We consider the presence of the two fluids separately. Okay. And how we will consider that the two fluids, they can be in bubbly flow, slug flow, churn flow? The interaction parameters are going to change. So, we will be incorporating these particular, the effect of the flow patterns in the interaction parameters, which shall be incorporated in the momentum equation written for phase 1, in the momentum equation written for phase 2. And from there we would like to see how the relative motion, the expression of relative motion can be derived, or the physics behind deriving the relative motion between the two phases. Now, let us then start writing the relative, or rather the momentum equation for the two phases. Now, if we consider the two phases, I will just write down the momentum equation. I will not go into much details. We will be dealing with this when we in the next chapter, when we deal with the separated flow model. I will just write down the basic equations and then see what best I can do with those equations in order to arrive at the kinematic constitutive equation to obtain J21. Now, whenever we write down the momentum equation, say maybe in the 3-dimensional form, well, I have it here itself. So, in the 3-dimensional form, you find it resembles probably the Navier-Stokes equation which you have already done, is not it? We have a time dependent term, we have an inertia dependent term, and then B1 and B2, they are the body forces, okay? Body forces per unit volume of the fluid element. That means, this is written for phase 1, this is written for phase 2. Okay? Now, for phase 1, naturally we consider unit volume of phase 1, fine, and here we consider unit volume of phase 2. Okay? And we find, so therefore, B1 is the body force, which is nothing but the gravitational force arising due to gravitational acceleration. So, this is B1 and B2 are the body forces per unit volume of components 1 and 2, which act on the respective components. Delta P, this is nothing but the pressure gradient. Okay. So, it is So, delta P, it is delta P, it is the pressure gradient, and it is the average pressure gradient or the bulk stress, which is, and it is suitably defined. It is usually the pressure difference of one or both the phases. And what about this term F1 and F2? Do you remember in Navier-Stokes what was the other term which was there? In Navier-Stokes, what was the other term? The other term was mu, is not it? And therefore, for fluid 1 it will be this, for fluid 2 it will be something else. So, this arose from the viscous terms, is not it? So, the point is, in this particular case, what is F1? F1, F2 are simply what is left over, which have to be incorporated in order to keep the account straight. This is what you should remember. Okay. Now, whatever, when you write down the momentum equation, body forces are there, pressure difference is there. Apart from this, whatever other term should come, which is not included in the pressure gradient, that is included in F1 as well as F2. So, therefore, F1, F2, they are simply incorporated in order to keep the account straight. Okay, if you observe this particular equation, you will find that F1 and F2 they have been incorporated, just they are just leftover forces per unit volume of the corresponding phase. They are simply incorporated to complete the momentum balance equation. Okay. So, therefore, when we were considering that it is incompressible Newtonian fluid containing only one component which is not undergoing phase change, then F1 will be equal to this. Okay. For Newtonian fluid, this you already know. For Newtonian fluid, incompressible one component and no phase change. This you have already derived. Okay. Now, usually what we find that these F's, they represent the average of the total force per unit volume that is not contained in pressure gradient. So, therefore, from where can F's arise? These F's, therefore, they can arise, in this particular case it was the wall shear stress. Okay. Apart from wall shear stress, they can arise from particle interaction. If there are if it is gas solid or liquid solid flow, then they can arise from particle interaction. They can also arise from hydrodynamic drag, isn't it? The drag between hydrodynamic drag, or in other words, it is the two phase drag. Okay. It can be between gas liquid, it can be between gas solid, it can be anything. So, it can arise due to the hydrodynamic drag. It can also, suppose there is evaporation, condensation, etc. Then what is happening? One particular phase, it is shifting from, say, the liquid phase to the vapor phase, or vice versa, isn't it? So, therefore, due to this, there is a momentum change of some portion of the fluid which is actually undergoing phase change. So, therefore, due to that there is some momentum change. So, that can also be incorporated in F. Okay. So, therefore, when there is a phase change, then forces due to momentum changes during evaporation / condensation. Or it can also be the apparent mass effects during relative acceleration. This can also happen. So, therefore, we find that whatever force, the leftover force which is there, which is not accounted for the pressure drop thing, that particular force, that is included in F1. So, therefore, when it is a Newtonian fluid and incompressible in single phase Newtonian fluid flowing through a pipe, then in that case you find that your F1 is nothing but it is the, it arises due to the wall shear stress, it is this particular thing. Now, when there are two phases, we find that it can arise due to number of situations. One is interaction between the wall and the fluid, maybe interaction between wall and fluid 1, wall and fluid 2. Okay. So, therefore, wall and fluid 1 should be included in this F1, wall and fluid 2 should be included here. It can be the hydrodynamic drag, that means fluid 1, fluid 2, that will also be included. Fluid 1 with respect to 2 will be included in F1, fluid 2 with respect to 1 will be included in F2. Okay. Now, when there is some particular condensation, evaporation, something, then some portion of the fluid, it is changing the phase. Now, we know that both the fluids are moving at different velocities. So, therefore, when you are changing the phase, say when evaporation is occurring, some amount of liquid is going into the vapor phase. Therefore, it is changing its velocity say from u1 to u2. Okay. So, due to this there has to be a momentum change due to this velocity change. So, that will be incorporated in F1 and F2. Okay. And apart from this, of course, the apparent mass effects during relative acceleration, that can also be included. So, whatever is not included in the pressure difference, that comes under F1 and F2. Agreed. Now, remember one thing, that quite frequently some portion of this of the effect is included in delta p, some portion is not included, only that portion has to be included in F1 and F2. So, these things you have to be quite cautious about. Always it is not very easy to segregate the forces which is not included in delta p and has to be included in F1, F2. These have to be kept in mind. Clear? So, therefore, whenever you write down a momentum balance equation, what are the things? Definitely there are the left hand side, and in the right hand side you have force due to weight of the fluid, simply the weight of the fluid which is included in B1, B2, then the pressure gradient and whatever is left over. That leftover thing, that depends on the exact flow situation. Okay, whether it is a change of phase situation, whether the hydrodynamic drag is important, whether the wall drag is important. So, F1, F2 they depend upon the actual flow situation, and according to the flow situation F1, F2 are different, and that is why using the two fluid model we arrive at different equations for different two phase flow situations. It is just because of the incorporation of F1 and F2. Correct. Now, usually as what we do, we usually take up the one dimensional approach. So, in the one dimensional approach, if we take the equations reduced to this particular form, which is quite evident to you. Now, in our case, if and for steady state conditions, if we find that for steady state conditions, when the inertia dominant conditions are there, then naturally the left hand side it disappears off, the left hand side which was here, this disappears off, and this portion becomes equal to 0, this portion becomes equal to 0, which I have written down. B1 is nothing but minus rho 1 g. I have considered the direction of flow to be positive or the upward direction to be positive. So, naturally your B1 becomes minus rho 1 g, B2 becomes minus rho 2 g. Okay. One dimensional, so therefore, they become minus dp dz. Okay. Now, in this particular case you tell me what should be included in F1 and what should be included in F2. Two phases are flowing. How they are flowing, how they are distributed, we are not concerned about it. But we know in whatever way they are flowing, in whatever way they are distributed, more or less what will happen, what will be the forces acting on fluid 1 other than the pressure drop force. It has to arise from the wall and it has to arise between due to the interaction between fluid 1 and fluid 2. These two forces have to arise. Okay. Now, considering the interaction of the fluid with the wall, naturally if the flow direction is in the upward direction, this interaction will be in the opposite direction, is not it? So, suppose you say that two fluids are flowing in this particular way. Okay. Since both the fluids are flowing, your FW1 and FW2 they should be in the downward direction, quite natural. Okay. The other thing is there will be interaction between the gas phase as well as the liquid phase. Okay. Now, assuming that the phase 2 is the gas phase or whatever it is, the phase 2 is the discontinuous phase, it has a higher velocity as compared to the liquid phase. Okay. So, therefore, the hydrodynamic drag, in which direction is it going to act? It will be acting in the direction opposite to the direction of motion for the gas phase, and it will be acting in the direction of motion for the liquid phase. Just like we decide your, so this should be the thing, is not it? And this F12, this is for the gas phase. Louder? Yeah, you can take it as F21 also, but if its mutual hydrodynamic drag, then in that case can't we say F12 equals to minus F21 equals to, or in other words the better thing will be, sorry, F21 is nothing but equal to minus F12. If you take F21 then it is fine, okay, you can take it in any direction, okay, but since I think that both these forces they are equal and opposite. So, therefore, F21 will be equal to minus F12. That is why I have not differentiated between these two. Otherwise, what I would have done, F12 for the liquid phase and F21 again in the upward direction for the gas phase, gas to liquid, liquid to gas. Now, we know that gas to liquid and liquid to gas, the hydrodynamic drags are equal and opposite. So, instead of F21 in the upward direction, I put F12 in the downward direction for the gas phase. Agreed? So, these are the forces which should act. Now, remember one thing, when I was defining this particular F, repeatedly I have told you one thing, that this is per unit volume of that individual phase. Do you remember this thing? That F1 is the leftover force per unit volume of phase 1, F2 is the leftover force per unit volume of phase 2. Agreed? Because both these equations, if you observe this equation and this equation, this is written down per unit volume of phase 1, this is written per unit volume of phase 2. Okay. Now, if we combine the mixture as a whole, then this small f1 and small f2, these things, if they have to be expressed in terms of per unit volume of the total mixture, then in that case, in what way it should be expressed? In that case, f1 for into 1 minus alpha is per unit volume of total flow field. Tell me if there is any doubt regarding this. F2 alpha is per unit volume of total flow field, where F2 is per unit volume of fluid 2, F1 is per unit volume of fluid 1. Is it clear to you? This particular portion, this particular transformation which has to be done, and this is denoted as capital F1, this is denoted as capital F2. Now, tell me whether this particular part is clear to you. What we did? First we found out that finding out the constitutive equation, it is much more advantageous to use the two fluid model. What is the two fluid model? We consider the two fluids separately, we write the momentum equation for fluid 1, we write the momentum equation for fluid 2. We did it in the 3-dimensional form in this particular way. We are always considering 1-dimensional form. So, this is the equation that we get. Now, in this particular equation, the only thing which has to be decided is regarding F1 and F2. Okay. Now, the point is this small f1 and small f2, they should consider what? Interaction of fluid 1 with the wall, interaction of fluid 1 with fluid 2. Agreed? For fluid 2, interaction of fluid 2 with the wall, interaction of fluid 2 with fluid 1. Agreed? So, therefore, it should contain something like Fw1 and F12 and the other one Fw2 and F21. Now, we know that the drags at the interfaces, they are equal and opposite. So, F21 equals minus F12. Okay. So, therefore, F1 should contain Fw1 and F12 and your F2 should contain Fw2 and minus F12. Now, what about the directions of these two things? Remember, regarding the directions, we have considered the upper direction as positive. Okay. So, therefore, if that is so, then in that case your Fw1, Fw2, they will be negative. Agreed? Acha, F12, it will be negative for phase 2 and F12, it will be positive for phase 1, assuming phase 1, assuming phase 2 travels faster, it is the lighter phase. On this assumption, these are the sign conventions which we can use. Agreed? Acha. After that, so therefore, in F1 and F2, in this F1 and F2, we have FW1, F12, FW2, F12 or minus F12. Fine. Now, you try to understand this F1 and F2, they were per unit volume of that particular fluid. Now, if we have to equate see FW1, FW2 or in other words F12 and F21, if we have to relate them, then they have to be expressed on one particular volume basis, is not it? It cannot be your volume of phase 1 per unit volume of phase 1 and per unit volume of phase 2. In that way, we cannot correlate F12 and F21, can we? Both of them have to be expressed on the basis of the same volume element. What will it be? The mixture volume. So, therefore, they have to be expressed in terms of per unit volume of the mixture. Do you agree? Now, if we take per unit volume of the mixture, then also your B1, that is going to be minus rho 1 g for vertical or else minus rho 1 g cos theta or something in this particular case. B2, it will minus rho 2 g cos theta. Okay, I will write it down. It's cos or sin, whatever the case may be. Okay, even if it is per unit volume of the entire flow field also, these things are not going to change. Do you get the point? Because per unit volume, these are the things which are remaining. Okay. But if we consider per unit volume of the flow element, then in that case the contribution from phase 1, contribution from phase 1 per unit volume of total, per unit volume of total flow, then this will naturally become F1 into 1 minus alpha. Do you get my point? Because in that per unit volume, there is alpha volume of phase 2, 1 minus alpha volume of phase 1. Okay, so therefore, the net contribution of 1 on unit volume of the total flow has to be F1 into 1 minus alpha. This we simply denote as capital F1. Similarly, contribution from phase 2 per unit volume of total flow, this will be F2 into alpha, which we denote as F2. Agreed? And where we find what is F1 equals to? F1, this will be equal to F12 minus Fw1, considering the signs. Clear to you? What is F2 equals to? This will be minus F12 minus Fw2, in other words minus F12 plus Fw2. Clear to all of you? Isn't it? So, therefore, instead of the F1 and F2 which we had got here, we have to substitute the equations which we have got. We have to substitute, instead of F1 we can substitute F1 by 1 minus alpha, and in that F1 by 1 minus alpha we can substitute this thing by 1 minus alpha. Anything you do not understand, you tell me to repeat. Similarly, instead of F2 we have to substitute F2 by alpha. F2 by alpha means this by alpha or this by alpha. Got the point? We have simply done that substitution and we have got this particular, we have accordingly I have written it down here also. We can make these substitutions and finally we arrive at these two equations for the two fluid model. Okay. Now, remember how have we accounted for the different interfacial phase distributions? By different expressions of F12. That is the way we have tried to incorporate the different interfacial distributions. Now, if we subtract one equation from the other, what do we get? If we subtract say equation 2 from equation 1 or something, then in that case what do we expect to get? You just subtract it and then tell me what is the equation that you are going to get on subtracting? We will get something like 0 equals to rho 2 minus rho 1 into G plus f 1 2 by 1 minus alpha plus f 1 2 by alpha, is not it? Just by subtracting we get this. Or in other words, if you want to express f 1 2, then this becomes 1 by 1 minus alpha plus 1 by alpha, this is rho 1 minus rho 2 into G. Or in other words, f 1 2 equals to what? It has to be alpha into 1 minus alpha into rho 1 minus rho 2 into G, is not it? And this particular equation, what does it represent? It represents a balance between fluid dynamic drag and buoyancy. Clear to all of you what I had tried to do? So, thing is, what we did first, we first wrote down the momentum balance equations and then we took it for steady state conditions under inertia dominant. If you see the PPT, you will notice that initially what we did it for the steady state inertia dominant conditions, we got this. Then we substituted F 1 and F 2. Okay. They will be having terms arising from hydrodynamic drag and wall shear stress. Now, usually what we have done is we have neglected the wall shear stress effects. Okay. We have tried to consider that particular situation where hydrodynamic drag is much more important. Under such a situation, we have written down the two equations. Okay. This is where we can neglect the hydrodynamic drag, we can neglect the wall shear stress, and basically this gives a balance between your buoyancy as well as the fluid dynamic drag. Then we have subtracted one equation from the other and we find that in the absence of wall effects, remember this is something very important, we have obtained this particular equation only under a situation where hydrodynamic drag is important and that is balanced by buoyancy. We have neglected your wall interaction, and definitely if this is applicable for gas liquid cases, if it is particle fluid cases, then we have also neglected particle interaction. It is just hydrodynamic drag and your buoyancy. From that particular balance, in the absence of wall effects under steady state conditions for inertia dominant cases, we have got this particular equation. Agreed? And from this particular equation, what do we find? This particular equation which has been obtained as a balance between buoyancy and fluid dynamic drag, what do we get? We find that F 1 2, it is a function of what? Component properties, it is a function of void fraction, and naturally void fraction is a function of interfacial geometry, and it also has to depend upon the relative motion, is not it? So, from this particular equation we get, let me see if I have it, no I do not have it. From this particular equation what we get? We get F 1 2, it is a function of, one is component properties. If you see it logically, you will find that these are the things on which F 1 2 depends. Then it has to be void fraction. Now, void fraction for all flow patterns, the relationship or variation of void fraction is not the same. Void fraction depends upon interfacial geometry and definitely relative motion. On these things F 1 2 has to depend. Now, for a given system, if we consider a given system, what do we find? For a given system, component properties, they become constant, is not it? And void fraction is dependent upon the interfacial geometry, your relative motion is dependent upon your interfacial geometry. So, therefore, for a given system F 1 2, that becomes a function of alpha and the relative motion. Do you get my point? Okay. Accordingly, we can also write, therefore, if f12 is a function of all these things, then j21 or j12, whatever it is, in whatever way, that should also be a function of your alpha and your system properties, as well as interfacial geometry. Yes or no? Tell me if you, because since I cannot interact much with you, so you should be telling me to repeat the things, or whether you have understood or not understood, you should communicate with me. Okay. So, therefore, from the basic equation which we had got, from this particular basic equation, what do we get? f12, it is a function of component properties, void fraction, interfacial geometry or interfacial configuration, and your relative motion. Relative motion, in whatever way you can express it, can be relative velocity, it can be drift flux, whatever it is. Okay. Now, if that is so, then automatically from there, from this particular equation, what do we get? Then j21 or j12, whatever, that should be a function of component properties, void fraction and interfacial geometry, right. And therefore, for any particular given system, j21, that is a function of, for if a system becomes fixed, then naturally your system properties become fixed, okay, and alpha and interfacial geometry, they are dependent on one another. Agreed. So, therefore, for a given system j12 or j21, that is a function of alpha only. Did you get my point? So, what do we find? We find that the relative velocity or the drift flux, both of them, u2j as well as j21, they are function of alpha only. They depend upon the drag forces acting at the interface as well as the interfacial geometry. So, therefore, your relative velocity as well as drift velocity, they are a function of alpha only, but this functional form, it should be different for different interfacial structures. Is this part clear to you? What did we deduce? f12 is a function of component properties. I think I have got a slide over this. Yeah, f12 we found out that it is a function of component properties, then void fraction, interfacial geometry, relative motion, etc. Okay. From this PPT also I have written it down. Now, if that is true, then in that case we find j21, that should also depend upon void fraction, system properties, etc., etc. Now, moment we fix up the system, then j21 should be a function of alpha only, and this particular functional form, the functional form of this particular equation, that should depend on interfacial distribution, or in other words, the type of equation which will describe the relationship between j21 and alpha, that should be different for different flow patterns. Agreed? And I will be giving you a set of the equations which are used for different flow conditions. But in general, with lot of experiments, what people have found that more or less your j21, that depends upon usually two things. One is, it can be expressed in terms of, say there is a discontinuous phase and a continuous phase. So, it depends upon the velocity of one maybe if it is bubbly flow, then one bubble, velocity of one discontinuous particle in an infinite medium of phase 1. Of velocity of one discontinuous particle means velocity of one discontinuous particle of phase 2 in an infinite medium of phase 1, okay, and it also depends upon alpha. and usually this particular functional form that people have obtained as J21 by u infinity equals to alpha into 1 minus alpha whole to the power n. Or in other words, you can also write it down as J21 equals to u infinity alpha into 1 minus alpha whole to the power n. So, what people have done? People have tried to find out some particular relationship between J21 and alpha. And what did people find? People found out that usually for a wide range of flow conditions, maybe for bubbly, for slug, for churn, for fluidized bed, for a wide range of conditions, people have found that a generalized functional form which is given in this particular way, the generalized functional form can be used for different flow conditions. What is the difference? When we take different flow patterns, only the value of u infinity and n are different for each of the flow patterns. If you take a fluid particle system, you will have some value of u infinity and n. For bubbly flow, some value of u infinity n. For slug flow, some value of u infinity and n. In this way, we account for different values of, or rather we account for the influence of the different flow patterns on J21 by using this particular equation. So, therefore, for all the equations, for all flow conditions, we find J21 is a function of alpha. The functional form can be represented by a generalized equation given in this particular functional form. Okay? And this is a general equation for all types of flow patterns which can be predicted by the drift flux model. But for different flow patterns, what we have? For different flow patterns, this value of u infinity and n are different. What is then? It is simply a function, a constant which varies with flow patterns. What is u infinity? It is the velocity of a single discontinuous phase in an infinite medium of the continuous phase. If it is gas, liquid, bubbly flow, it is the rise velocity of a single bubble in an infinite liquid medium. If it is a fluidized bed sort of a system, then in that case it is the velocity of a single solid particle or the terminal velocity of a single solid particle falling in an infinite medium of the fluid. If it is slug flow, then u infinity is the velocity of a single Taylor bubble in an without the wall effects. So, accordingly u infinity is different for different flow situations, n is different for different flow situations, and accordingly by incorporating different values of u infinity and n, we can find out J21 for different flow situations, correct. Now, for certain cases the value of u2j and J21 have been proposed in several textbooks. I have just written down these particular equations for your convenience. Okay. So, for the viscous flow regime, these equations they are just for your for you to note, you need not memorize them or you need not remember them. For the viscous regime, this is the equation. Then for the Newton's regime, this is the equation, and then for distorted fluid particle, again we have different things. For the churn turbulent flow regime, this sort of, these are equations for u2j. We know that alpha into u2j is nothing but J21. Okay. And just I would like to mention what is this churn, and for the bubbly for the slug flow probably this is the equation. Yeah, for the churn turbulent flow regime. Churn turbulent flow regime is a bubbly flow pattern where the bubbles can be of different sorts of sizes and shapes. It is just a transition between the bubbly flow pattern and the slug flow pattern. Normally, what do we say? We say that for the bubbly flow pattern, we have bubbles of this sort. For the slug flow pattern, we have something of this sort. Okay. Now, for the churn turbulent flow pattern, we can have a wide type of bubbles, we can have cap bubbles, it can be a totally erratic distribution resembling the churn flow regime to some extent. Okay. So, therefore, usually this particular flow pattern which is a transition between these two, this is usually known as the churn turbulent flow regime. Okay. And we find that for number of situations we neither operate here nor operate here, we operate in the churn turbulent flow pattern. This is one type of bubbly flow pattern which marks the transition between the bubbly and the slug flow patterns. Okay. Now, for this particular case people have proposed this equation for UTJ, and people have said that when it is gas liquid system root 2 is fine, and when it is liquid system, then instead of root 2 1.57 is better. So, these are simply empirical equations. In case you have to sort out any problem with drift flux model, depending upon the situation, you select a particular U2j. From this U2j you select you find out a particular J21, that J21 you apply, and then you find out alpha rho mixture and whatever other things are there. Okay. And this particular equation, this is for the slug flow pattern. So, for different flow patterns we have different particular flow equations, or rather different expressions of drift velocity. Depending upon your case, you are supposed to select it and you are supposed to do it. But just remember, whatever equation you use, whatever you do, more or less we find that this particular equation can be used. So, naturally U2j becomes this equation. U2j people have proposed it is a function of u infinity and the hold up of the continuous phase. From there people have found J21 can be obtained from this particular expression, and where u infinity and n depend upon the different flow conditions. The only two limiting conditions which have to be taken into mind while using this particular equation is that J21 has to be 0 at alpha equal to 0, J21 has to be 0 at alpha equals to 1. These are the two limiting conditions which have to be agreed upon by all equations which we use to find out J21. Okay. So, this was all about the kinematic or rather how the kinematic constitutive equation has been proposed to find out J21. So, now what we have? We have two equations, we have two unknowns. What are the two equations that we have? One equation was one which we derived from the drift flux model, which gave us J21 equals to J2 plus alpha j, isn't it? And the other equation we have J21 equals to u infinity alpha into 1 minus alpha whole to the power n. There are two unknowns, one is J21, one is alpha, and we have two equations. So, we can solve them simultaneously, and we can get a value of alpha, we can get a value of J21, and from there we can get value of different mixture properties. Agreed? Now, how we will solve them? Simultaneous solution is definitely one, but we would prefer a graphical solution, because graphical solution will enable us to take into account the different flow directions of the different flows. It will also help us to account for the different the effect of varying the phase flow rates. So, in the next class we will take up these two equations, we will try to solve them, or rather the simultaneous solution will be done by a graphical technique, and we will see what are the different information that we can get from those graphical technique, what are the different ways of representing the two equations graphically, and accordingly we will proceed. Okay, thank you very much.